Okay, so in this video we are going to learn this RC circuit. We will connect a battery with this RC circuit, whose EMF is E, and we will derive an equation. Then from that equation we will obtain a graph of I versus time graph, and we will see that the current across this resistor and capacitor will exponentially decay, and theoretically when time is infinity the current across this capacitor is 0 ampere. That means when the time is infinity the capacitor is acting like an open circuit, because when you will put a open circuit across this capacitor the current will be 0 ampere. So at t is equal to infinity the capacitor is acting like an open circuit. So we will discuss these things in this video. So let's start. Okay, so first we have to learn the characteristic of this capacitor. So let's say it's an capacitor and the charge stored plus q and minus q in these two plates, and more the charge stored in this plate, the more the voltage difference across these two plates. So from this we can see that the q is proportional to v. Higher q we will get the higher the q we will get higher the v. So here now we have to put in proportionality constant c. Here c is called capacitance. You know, it's the capacitance of the capacitor and its unit is in farad, but farad is a very large unit, so we use microfarad. Okay, now the main thing is we have to differentiate with respect to time, as c is constant, so let it go. Let's differentiate the voltage difference. Now when we differentiate the charge with time, with respect to time, we will get the current. So I is equal to c dv by dt. Okay, so this is the equation for the current across the capacitor. We will use it later. Now let's draw the RC circuit. So it's the RC circuit, and let's connect this with the battery whose EMF is E. Okay, so if we assume that the voltage difference across this capacitor is small v, then the voltage difference across this R will be E minus V. Now as the current through resistor and current through capacitor is same, as they are connected in series, we can write I is equal to for current across this resistor we can write above E minus V, and in the denominator we can write the resistance R. Again for the current across this capacitor we can write the equation I have already derived. I is equal to c dv by dt. So I is equal to c dv by dt. As these two currents are same, we can write these things equal. So E minus V by R. Okay, so we have to solve this equation by some little bit integration. Okay, so let's do it. So rearrange the equation like this. Place dt to the left hand side, dv, then E minus V to the right hand side, so it's E minus V. Okay, now we can write this as 1 by RC dt. Then let's write it E minus V as minus V minus E. Okay, now we have to integrate these two terms, left hand side and right hand side, and we have to place lower limit and upper limit also. When time is 0, the difference across this was v naught when time was 0, and when time is t, the difference across this capacitor, let's say v. Okay, integrate. If we integrate dt, we will obtain t, and on the third bracket we will write the limit, lower limit and upper limit, and if we integrate the right hand side we will get ln v minus, and then in third bracket we have to write the okay, now it's so easy. It's upper limit, place it here, minus then 0. here, it's the formula's minus, then place V naught here. Now rearrange this equation, 1 by RC dt. What we can write this as ln something minus ln something is equal to ln V minus E divided by V naught minus E. Now we want to obtain V, so let's find V. So if we took the minus on the left hand side and then we will get e to the power minus 1 by RT, or we get exponential because the ln is placed to the left hand side. Okay, so V minus E, then V naught minus, and then again place this V naught minus to the left hand side. So we get E plus V naught minus E to the power minus T by RC. So it's our equation, and for simplicity, if we assume that when time was 0, initially V naught, that is the voltage across was 0, then we will get a simplified equation. Okay, and if we take E common, so E1 to the power minus T by RC. Okay, so this is our equation, and we will now study this equation. So what have we done? Let's revise that. We have drawn an RC circuit, okay, and then at time is equal to 0, we place a battery here, connect the battery here, and then we obtain the formula for the voltage across this capacitor, and the capacitor's voltage is E 1 minus e to the power, let's write it here, V 1 minus e to the power minus T by RC. Okay, so let's assume when T is equal to 0, if I 0, then e to the power 0 would become 1. So the capacitor voltage is there 0, normal. And when T is equal to infinity, something interesting will happen here. When T is equal to infinity, let's write the equation again, 1 minus, we know that e to the power minus something, we can write it e to the power 1 by e to the power something. Okay, now as T is tends to infinity, so e to the power infinity is again itself infinity, and 1 by infinity is equal to 0, so we can write V is equal to E. Okay, so we have obtained, if we obtain a graph of the voltage versus time graph, we will see that when the time was 0, voltage was 0, but when the time was infinity, the voltage is E. That is, the graph will try to reach the E but never will cross E. When the time is infinity, the voltage will be E. That means when we connect a battery with capacitor, the voltage across the capacitor will become the EMF of the battery. Okay, now talk about current. What is the equation of current? I is equal to use this equation. I is equal to E minus V by R. E minus V by R. Okay, when T is equal to 0, initially, see, T is equal to 0, the voltage across the capacitor was 0, and in that time I is equal to E by R. Okay, but when T tends to infinity, let's see what was the voltage. The voltage across the capacitor is equal to the EMF of the battery, and in that time I is equal to 0, right? And it was expected that at T is equal to infinity, the current across the capacitor is 0. Now if I write the equation, let's put here I, then here t, we will obtain a graph that at t is equal to 0 the current was E by R, but as time increases the current decreases and tries to become 0 but never will become 0, but theoretically when time is infinity current will become 0. And if I want to write the equation here, we can write I is equal to E by R minus 1 by R V. And now put the equation of V, this V here, E 1 minus e to the power minus t by RC. Now take a common E by R, then we will have 1, then 1 plus e to the power minus t by RC, and you will see that the current's equation is this. So if you analyze this equation, you will also obtain this graph, and see the graph is actually an exponentially decay graph. That means the current will decrease exponentially. Okay, so theoretically the current will 0 at t is equal to infinity. But what happens practically? Practically the current becomes 0 not in time infinity. Rather than we observe that in a very small time the current becomes infinity. Let's talk about practical what we do in practical situation. Let's say when time, let's say we draw a RC circuit again. The capacitance is 1K, sorry, the resistance is 1K, the capacitance is 47 microfarad, and the voltage is, let's assume 5 volt. Okay, so when t is equal to 0, the voltage across this capacitor is 0 volt. That is, we can say that the capacitor is not charged. Now we want to charge the capacitor, and to do this we have connect a battery here. Let's when time is 5 RC, that is 5 into 1K into 47 microfarad, time is 0.235 second. Let's see what will be the voltage. So V is equal to, let's write the equation here, E 1 minus e to the power minus t by RC. T is equal to 5 RC, then the RC numerator and denominator will get off. Now if I calculate this voltage, we will get okay, I calculate this and we will get the voltage 4.9663 volt. Okay, it was not infinity, it was in the time of 5 RC, which is very small, 0.235. We get a voltage 4.963, that is approximately 5 volt, right? That is approximately similar, same as battery's EMF. Okay, now let's try to find the current, and to find the current we will use the equation, we will use this equation. Okay, we will use this equation and we will get, let's put all the information here, E is equal to 5, V 4.966, resistance is 1K. You will see that we will get a very small current. Yes, and the current is 3.3689 into 10 to the power minus 5 ampere, that is near to 0 ampere, right? So we get a very small current, and you see that instead of t is equal to infinity, we use t is equal to 5 RC and 5 times RC, and in this time we get a very small current. So practically we say that the capacitor is fully charged, the current is 0 ampere when time is 5 RC. And another thing is, in this case capacitor is acting like an open circuit. Why this is an open circuit? Because when we use an open circuit instead of capacitor, the current will be 0 ampere. So as using open circuit the current is 0 ampere, we can say that after some time the capacitor will act like an open circuit. Okay, so after in next video we will see that we have charged the capacitor, right? We have charged the capacitor and the voltage across this capacitor is 5 volt. Now if we connect a resistor with this capacitor, what will happen, how the capacitor will discharge, we will see this in the next video. So goodbye.